This recording is going to cover the first half of Module 14 in physics, which is on electrical potentials. So first of all, just to give you a general overview of what this chapter is going to cover, I'd like for you to imagine that you have a charge that is sitting by itself in space, and we have called that charge Q. And we want to know if I were to place another charge close to this Q, so somewhere within the sphere of influence of Q, what's going to happen to that other charge? So in other words, what will be the impact of that other charge on it? So in general, that's what we're going to be talking about in this chapter. So in other words, it allows us to imagine that if you have this charge Q is affecting the space around it, in some way, and whenever you put another charge in near to this charge Q, how is Q going to affect that charge? So that's in a nutshell what we are going to be talking about in Module 14. So we learned about electrostatic force last chapter, and so we're going to be looking at how do electric charges move when there's an electrostatic force. So you have this force, and how does that cause these electric charges to move? And of course, going back to previous things that we had studied, because these charges are moving, then we would say that they have kinetic energy. So you might wonder what the practical application of all of this is, and that is that, you know, when charged particles have kinetic energy, then we can use that kinetic energy to do work. So the kinetic energy of electrons moving in a wire, for example, we can convert that kinetic energy into light or heat, or into energy that's used to run a motor or other application. So that's the practical application, is taking the kinetic energy of these electrons and converting them into other forms of energy that can be used. So in this module, we are going to be looking at the relationship between a stationary particle, a stationary charged particle, and then looking at how that charged particle impacts other charges that are brought near to it. So if we start with a charged particle that is at rest, or we say it's stationary. Let's say we have a positive charge that is stationary, and then if we bring close to it another charge that is negative. So both of these charges, in this case, if we imagine them starting out stationary, then these charged particles have potential energy when they are at rest. But because these charges have, because they have their charges are opposite, the positive charge is stationary, so it cannot move. But because the charges are opposite, they're going to be attracted to each other. So this particle is going to move toward that particle. And so we know then that because of the first law of thermodynamics, we know that energy cannot be created or destroyed. It can only be changed from one form to another. So when these charges went from being at rest to being attracted to each other, so that this negative charge moves toward the positive charge, well, what happened? Well, this potential energy got converted to kinetic energy. Okay, so these are some of the things that we are going to be working with. So I've assumed here that these charges, that that there is potential energy in this system, and so then you might ask, well, where did that potential energy come from? Well, the potential energy comes from something that we call electric potential. And electric potential we designate with a capital V, and it is equal to K times Q divided by R. So K we have already seen is Coulomb's constant. You'll be given the value for that. Q is the fixed charge. So it's the magnitude of the fixed charge, and we'll see in a moment that unlike when we calculate electrostatic force, when we're calculating electric potential, you need to include the sign. So previously we have only included the magnitude. Now we need to include the sign, and that we'll see why that is true in just a moment. And then R is the distance between the fixed and the stationary charge. Okay, so keep this equation in your arsenal, and that's an equation that we will be using throughout this module. So let's look then at the units that would be involved. The unit for K is a Newton meter squared per Coulomb squared. The unit for Q is going to be in coulombs, and the unit for R is going to be in meters. Okay, so one of the meters will cancel, one of the coulombs will cancel, and we are left with Newton meters over coulombs. Now I just said previously that the electric potential, or the potential energy, comes from electric potential, and yet the unit for potential energy is a joule, which is a Newton meter. So the units for electric potential and the units for potential energy are not the same, and therefore electric potential is not the same as kinetic energy, potential energy. So electric potential is not potential energy. Again, hang on, and we'll try to make sense of that, but remember that electric potential is not the same as potential energy. So, let me back up here. So the units for electric potential is a Newton meter over coulombs, and we refer to that as a volt. Okay, so if you have like a 1.5 volt battery or 9 volt battery, it's a Newton meter per Coulomb. So we have this electrostatic force that is generated between two particles. That's what we did in the last module. So if we want to see the effects of that electrostatic force, we have to consider both of the charges, not just one. And yet in our previous equation, we only considered one charge. So let's think about this. So if you have two charges, and those charges the kinetic energy of these charges is going to come from the potential energy. So the potential energy has to depend on both charges, because if we have those two charges and they are accelerating toward each other or away from each other because they're being attracted or repelled from be repelled from each other, the magnitude of both of the charges is going to influence the acceleration. So if their kinetic energy is going to be influenced by both charges, then we also know that the potential energy is also going to be affected by both charges. So we can't ignore that second charge. So to get that second, to account for the influence of that second charge, then we have an equation for potential energy. And potential energy is equal to Q times V. Okay, so it's is equal to Q times the electric potential. So remember, this electric potential accounts for the fixed or stationary charge. Because remember, V was equal to K times Q divided by R. Okay, so, or K times Q divided by R. So with calculating the electric potential, we are accounting for the fixed charge, and then this will be the other charge. Okay, so remember I said that potential energy is not the same as electric potential, because electric potential only accounts for one charge and not for the other. Okay, so now if we look at the units now, so potential energy is equal to, that Q will be in C, in coulombs, and we said that V is in Newton meters over coulombs. So the coulombs are going to cancel, and you are left with Newton meters, which is a what? A joule. And that is the unit for energy, the unit for potential energy. Okay, so the way that we calculate the potential energy, accounting for both charges, is that potential energy is Q times V. Okay, so that's another equation that you should keep in your toolbox for this module. Okay, so let's say that we have a positive charge here, and we have a negative charge over here. this charge is stationary, and this charge is able to move, free to move. Okay, so what's going to happen? Because they are opposite charges, this charge that is free to move is going to be attracted, and it will move toward the stationary charge. So what's going to happen to the R value, the distance between them? Well, obviously, as this charge moves toward here, R is going to change. And if R changes, that is going to change V, right? So V will change, because remember that V is equal to K Q divided by R. So any change in R is going to change V. And if I change V, then what else will change? Well, if I change V, then potential energy is going to change, because we said that potential energy is Q times V. Okay, so as these charges move, as this charge moves toward that one, R is going to change, therefore V will change, and if V changes, then potential energy will change. And so in what way are they going to change? Well, if you think about it, the V is just based on the stationary charge, right? Which is negative. So the value for V is going to be negative, and the value for the other charge is going to be positive. So when we multiply a positive times a negative, potential energy is going to be negative. So what does that mean? Well, a negative potential energy means that the potential energy will be decreasing. And that makes sense, because these particles started stationary, so the energy that they possessed was just potential energy. But then as the positive particle starts accelerating toward the negative charge, and as it gets closer, it's going to continue to accelerate. Well, then what's happening? The potential energy is being converted to kinetic energy, the energy of motion. So potential energy is decreasing, which means that kinetic energy must be increasing. And according to the second law of thermodynamics, or the first law of thermodynamics, that has to happen. We could look at another example. What if we had two negative charges, and so we have these two negative charges, and what if so this is the stationary one here. And what if we give this moving charge an initial velocity in this direction? So we're gonna cause this particle to move in this direction. So we're going to give it an initial velocity. So it's going to have kinetic energy, right? And it's going to have kinetic energy in that direction. Well, these charges, because they're the same charge, they're going to be repelling each other. So as we will give this particle an initial velocity in this direction, but those particles are going to be repelling each other, so that eventually even though we gave it an initial velocity in this direction, it will eventually reach a point and it's going to stop, and then because of the repulsion, it's going to turn back the other way. So what happened there? We started out with kinetic energy. That kinetic energy is going to get less and less and less until it stops, it's going to reach zero. And then then all that energy will be, at that point, will be potential energy. And then because of repulsion, the particle will turn around the other way. So now if we look at our equations in this case, so the potential energy is equal to Q times V. Well, because the stationary charge is negative, V will be negative, and Q is also negative. So now potential energy is what? It's positive, which means that it is increasing. And if it is increasing, then kinetic energy is going to be decreasing. Okay, so that initial kinetic energy that we gave to that particle, it will decrease, and as it's decreasing, you're going to be increasing the potential energy. Again, in accordance with the first law of thermodynamics. Okay, so let's do a few problems. Let's just start by doing on your own 14.2. Oh, actually, let's do 14.1 first. So on your own, 14.1. This tells us that we have a negative 2.1 millicoulomb charge. So negative 2.1 is millicoulombs. So since we work in coulombs, I'm going to go ahead and convert that to coulombs. And we're told that this cannot move. So this is our stationary charge. And then we have a positive 4.1 coulomb charge that is free to move. And these two charges are placed 61 centimeters or 0.61 meters apart. And we want to know what is the electric potential at that point. So we know that V is equal to K times Q divided by R. And the Q in this case is the stationary charge. So V is going to be equal to 9.0 times 10 to the 9th Newton meters squared per Coulomb squared times the stationary charge, which remember we include the sign now, 2.1 times 10 to the negative 3 coulombs, and then we will divide that by our radius, which is 0.61 meters. Okay, so one of these meters will cancel. One of these coulombs will cancel. So that'll cancel and we'll be left with that there. So we have Newton meters over coulombs, which is a volt. And what you should get for that V value then is that V is equal to negative 3.1 times 10 to the 7 Newton meters over coulombs or volts. Okay, so that's just a simple application of our equation for electric potential, remembering that you need to include the sign as well as the magnitude of the charge. Okay, now let's look at on your own 14.2. Okay, and on your own 14.2 tells us that we have a positive 7.9 millicoulombs. Again, I'm going to go ahead and change that to coulombs charge. And it is placed 1.1 meters away from a negative 2.3 coulomb charge. And this is the stationary charge. And then the question asks us, what is the potential energy in this charge? Okay, so we know that potential energy is equal to Q times V. Okay, so the first thing we have to do is calculate V. So V is equal to 9.0 times 10 to the 9th Newton meters squared over Coulomb squared, and then times the charge of the stationary charge, including the sign, and then the radius between them is 1.1 meters. Okay, so one of these meters will cancel, that one of those coulombs will cancel, we'll be left with Newton meters over coulombs, which is a volt. And so what you should get for V there is negative 1.9 times 10 to the 10 volts. And volts or Newton meters over coulombs. Okay, so now we know that V, so now we can plug that number into our equation for potential energy. So potential energy, now we're going to include the other charge, so it will be equal to 7.9 times 10 to the negative 3 coulombs times the V that we just calculated. Negative 1.9 times 10 to the 10, and I'm going to put this in as Newton meters over coulombs so we can see what happens to the units. So now potential energy is equal to negative 1.5 times 10 to the 8 so coulombs are going to cancel, and we will be left with Newton meters, which is a joule. So 1.5, negative 1.5 times 10 to the 8 Newton meters or joules. Okay, so that is 14.2. Okay, so we've already said that potential energy when we get a decrease in potential energy, then that is going to lead to an increase in kinetic energy, so that the first law of thermodynamics holds true. So when we have charges moving, like the ones that I just previously talked about, when you have a change in potential energy, that's going to be equal to it means you're going to have a change in the electric potential. So how does the kinetic energy in this situation change? So delta V is equal to what? VF minus VI. So it's the final electric potential minus the initial electric potential. So then this is what we end up with then, is that the change in potential energy is equal to the moving charge times the change in times the change in the electric potential. Okay, so let's go ahead and let's work through a problem with this, and then so that you can see how this is applied. So we're looking at example 14.2, and we are told that we have a negative 5.6 millicoulomb charge. I'm going to change that to coulombs. And that charge is free to move, and the fixed charge is 4.8 millicoulombs, so times 10 to the negative 3 coulombs. So this is the fixed charge. And these two charges are 0.6, they're 68 centimeters apart. So that's going to be 0.68 meters from each other. And then we are asked if the freely moving charge, so if this charge moves toward this charge, if it moves 15 centimeters, which is 0.15 meters toward it, then what will be the change in potential energy? And did the potential energy increase or decrease? Okay, so they start out 0.68 meters apart. This charge is going to move, this moving charge is going to move towards this one, 0.15 meters, and then we want to know how much did the potential energy change there. Okay, so let's go back to what we know. So we know that V is equal to K times Q divided by R. And we also know that the change in potential energy is equal to Q times the change in V. Okay, so the first thing we've got to do is we need to figure out what is the change in V. And we've already said that delta V is equal to VF minus VI. Okay, so let's calculate these two values so that we can get the change in electric potential. So let's do VI first. So VI is going to be K times Q divided by R. So it's going to be 9.0 times 10 to the 9th Newton meters squared over Coulomb squared times the charge of the stationary charge, 4.8 times 10 to the negative 3 coulombs. And then we're going to divide that by the distance between the two particles, and for the initial ones it's going to be 0.68 meters. Okay, so if we do the math on this, one of these meters will cancel, one of these coulombs will cancel, Newton meters are coulombs, which is a volt. So what we get for VI then is 6.4 times 10 to the 7 volts. Okay, so that's VI. Okay, now let's go ahead and do VF. So VF, the final electric potential, again, it's going to be K times Q divided by R. K is going to be the same. It's at state, it's 9.0 times 10 to the 9 Newton meters squared over Coulomb squared. And then Q, again, is going to be the charge of the stationary charge. It's a positive charge. And now what's R going to be? Okay, so we said that R started out at 0.68, but then it said that it was going to move 15 centimeters or 0.15 meters toward the stationary charge. So if it's moving toward, then they're going to be closer together. So we're going to subtract 0.15 meters, and we will get 0.53 meters. Okay, so the new radius will be 0.53 meters. Okay, so one of these meters will cancel, the coulombs cancel, Newton meters over Coulomb, which is a volt. And what we get for the final then is 8.2 times 10 to the 7 volts. Okay, so now we have VF and we have VI, so we can calculate delta V. So delta V is equal to VF minus VI. VF was 8.2 times 10 to the 7 volts, minus VI was 6.4 times 10 to the 7 volts. So that delta V is equal to 1.8 times 10 to the 7 volts. Okay, so that's delta V. Now all we have to do is take that value and plug in the lowercase q, which is the charge of the stationary, the moving charge. Okay, so delta PE, the change in potential energy, is equal to the charge of the moving charge, including the sign, times delta V, which we calculated as 1.7 times 10 to the 7 Newton meters over coulombs. That's what a volt is. So the coulombs will cancel. You'll be left with Newton meters, which is a joule, and that's a unit for energy. So what we will get is that the change in potential energy is negative 1.0 times 10 to the 5 joules. So what does that mean? Because it's negative, it tells us that the potential energy decreased 1.0 times 10 to the 5th joules. Okay, and again, that should make sense because if we have a negative charge and a positive charge, this one can't move. This is stationary. So they possess a certain amount of potential energy, but they're going to be attracted to each other. So this charge is going to start moving toward that charge. And when it does that, potential energy is going to be converted to kinetic energy. And we specifically calculated what will happen to the potential energy when it has moved 15 centimeters or 0.15 meters. When it has moved 15 centimeters, the potential energy will have decreased by 1.5 times 10 to the 5th joules, which means that kinetic energy would have increased by an equal amount. Okay, let us do, I'm going to save on your own 14.3 and 14.4 for you to do, and we will go over those in class next week, or I will record those and let you see those. Because we have one more thing that we have to do, so now we're going to pull kinetic energy into the picture. We've talked about kinetic energy, that if potential energy decreases, then kinetic energy has to be increasing. But let's see how we can apply that now. Okay, so I'm going to look at on your own, or I'm going to look at example 14.3. And we will work through that, as well as a couple more examples. So example 14.3 says we have a negative 15.1 millicoulomb charge. Go ahead and go and convert that to coulombs. Its mass is 2.34 kilograms, and it is placed 13 centimeters away. So I'm going to go ahead and convert that to meters, 0.13 meters away from a fixed negative 2.0 coulomb charge. Okay, so this is our fixed or stationary charge. And this says if the particle starts at rest, at what speed will it be moving when it is 95 centimeters away from the fixed charge? Okay, so so they're starting at rest, and so first of all, because they have opposite signs, they're going to be repelled from each other. So if this is the fixed charge, then this charge is going to be repelled and it's going to move away. It's going to be moving, the moving charge will move in the direction of the arrow that I drew. And what we are asked is at what speed will it be moving when it is 95 centimeters away, or 0.95 meters away? At what speed will it be moving? Okay, so when it is at rest, it possesses potential energy. And once these charges repel each other and this moving charge begins to move, then potential energy is going to be converted to kinetic energy. Okay, so let's look then at, I should have kept that charge up there. So the other charge is a negative 15.1 times 10 to the negative 3 coulombs. Okay, so we first have to calculate what is the potential energy. And we know that potential energy is equal to Q times, the change in potential energy is equal to Q delta V. Okay, so let's first calculate delta V. So VI and VF. Okay, so VI is going to be equal to K times Q divided by R. So 9.0 times 10 to the 9th Newton meter squared over Coulomb squared times the fixed charge, negative 2.0 coulombs, and then R, it will be the distance that they were originally apart. That's 0.13 meters. Okay, so one of these meters is going to cancel. Coulomb, you'll be Newton meters per coulomb, so that's going to be a volt, and what you should get for that is negative 1.4. So remember, keep the sign in there. Negative 1.4 times 10 to the 11 volts. Okay, that's VI. VF, 9.0 times 10 to the 9th Newton meter squared over Coulomb squared times the stationary charge, 2.0 coulombs. And now what will R be? Well, the question asks, what will the velocity be when, or how fast will the charge be moving when it is 0.95 meters away? So our distance is 0.95 meters. So then what we get for VF is negative 1.9 times 10 to the 10th volts. Okay, so now we can, with that information, we can calculate the delta V. So delta V is VF minus VI. So it's going to be negative 1.9 times 10 to the 10 volts minus a negative 1.4 times 10 to the 11 volts. Okay, so the negative minus a minus is a plus. So delta V comes out to be 1.2 times 10 to the 11 volts. 1.2 times 10 to the 11 volts. Okay, so that is delta V. Okay, then now we know, so now we can go ahead and do the change in potential energy. So the change in potential energy, so delta PE is equal to Q delta V. Okay, so we just figured out what delta, or why did I put delta X, delta V. Okay, so we just figured out that delta V is 1.2 times 10 to the 11 volts. And now Q will be that other charge, the moving charge. So we'll put that in there. Negative 15.1 times 10. 10 to the negative 3 coulombs. Okay, and this, let's go ahead and change this volt to a Newton meter over a coulomb so you can see the coulombs cancel. So the change in potential energy is equal to negative, so a negative times a positive is negative. So it's 1.8 times 10 to the 9th joules. So what does that mean? Potential energy is negative, which means that it decreased 1.8 times 10 to the 9th joules by the time when this charge was 0.95 meters away from the other charge. The potential energy had decreased 1.8 times 10 to the 9th joules. Well, what does that mean? That means that the kinetic energy had increased 1.9 times 10 to the 9th joules. They started stationary, so that means the kinetic energy started out at 0, but it is now 1.9 times 10 to the 9th joules. So how does that allow, now the last bit of information that we wanted to know how fast that particle was moving. Well, we know that we know from previous study that kinetic energy is equal to 1/2 mv squared. Okay, so we know the kinetic energy, we know the mass, so we can calculate the velocity. So kinetic energy divided by 1/2 the mass, and if we take the square root of that, that is going to equal V. So we calculated the kinetic energy as 1.8 times 10 to the 9th joules. So 1.8 times 10 to the 9th Newton meters divided by 1/2 and divided by the mass, which we were given as 2.34 kilograms. I'm going to take the square root of all that to get the velocity. So let's go ahead and change this just so we can see units. So a Newton, a Newton meter. A Newton is a kilogram meter per second squared. And then we had it was a Newton meter. So kilograms will cancel, and we'll have meters squared over seconds squared. So when you take the square root of that, you will get meters per second. So what you should get for the velocity, when you do that, you should get that V is equal to 3.9 times 10 to the 4th meters per second. Okay, so when that moving particle is 95 centimeters away from the stationary particle, it will be moving at 3.9 times 10 to the 4th meters per second. Okay, I want to do one more. Let's see which one is a good one to do. Let's do the, we're going to do an example problem that's a little bit different than others, or just one little wrinkle added to it. So now we have a negative 0.21 millicoulomb charge. So negative 0.21 times 10 to the negative 3 coulomb charge, whose mass is 3.1 kilograms. And it is given an initial velocity of 15.1, or just 15 meters per second away from the other particle, which is a positive 0.45 millicoulomb charge. That's times 10 to the negative 3 coulombs. And we are told if they are originally 33 centimeters, which is 0.33 meters away, how far away will the particle be able to travel before being pulled back toward the stationary charge? Okay, so let's think about this. So we have a negative charge here, and we have a positive charge here. This is the stationary charge. So they're going to be attracted to it, and they are 0.33 meters apart. Okay, so this is the stationary charge, and because they are opposite, they're going to be attracted to each other. So this charge would move, the negative charge would move toward the positive stationary charge. However, we are going to start by giving this charge an initial velocity in the other direction. So we are going to send it moving in this direction at 15 meters per second. Okay, so it's starting with kinetic energy, right? And it will move in that direction. However, it's going to move in this direction because of the initial push that we give it, but this positive charge is going to be pulling it back. So what will happen is that this charge will move in this direction, but it's because of the pull of that positive charge, it's going to that the kinetic energy is going to be slowing down, and then it's going to reach a point where it's going to stop, and then it's going to head back in the other direction because of the pull of that positive charge. So starts with kinetic energy. That kinetic energy will be decreasing, 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 decreasing because of the charge, the pull of this positive charge. It will, so the kinetic energy is decreasing, the potential energy is increasing until it gets to this point, then it's going to stop. So that now it only has potential energy, and then it's going to head back in the other direction due to the pull of that positive charge on it. Okay, so we're taking that kinetic energy, converting it to potential energy, then that potential energy be converted back to kinetic energy as it heads in the other direction. So the question they are asking us is, how far away is it going to go until it gets pulled, until it stops and pulls back in the other direction? So in other words, what we are being asked is, how far away will it be when the potential, and when it's all potential energy, when all the kinetic energy has been converted to potential energy? Okay, so I hope you understand that, the logic there, or the thinking behind the question. Okay, so it starts out with kinetic energy. So we can go ahead and calculate its kinetic energy. So the kinetic energy is equal to 1/2 times the mass times the velocity squared. So 1/2 times the mass, which was 3.1 kilograms. And then we're going to square the velocity, which is 15 meters per second. So the kinetic energy will be equal to 190 meters per second, or 1.9 times 10 squared meters per second. Okay. Oh wait, I'm sorry, I'm on the wrong problem. What we will get for kinetic energy is that the kinetic energy will be equal to 350 joules. So 3.5 times 10 squared Newton meters. Okay. Because you're going to have kilogram meters per second squared times meters, which is a Newton meter. Okay, so the kinetic energy is 3.5 times 10 to the 10 squared Newton meters. So what does that mean? Well, we want to know if that kinetic energy, if the kinetic energy decreases by 3.5 times 10 squared Newton meters, then the potential energy has to increase by that much. So the potential energy would be equal to 3.5 times 10 squared Newton meters. Okay, so the kinetic energy is going to be decreasing by that much. So this has to be increasing by that much. Okay, so that's delta PE, right? That's the change in potential energy. We went from 0 potential energy up to this much. Okay, so what can we do with that now? Well, we know that the change in potential energy is equal to Q delta V. Okay, so now we know this, and we know the charge. So we should be able then to figure out delta V. Okay, so delta PE divided by Q is going to equal delta V. Calculated the change in potential energy as 3.5 times 10 squared Newton meters. And we will divide that by our charge, the moving charge, which was negative 0.21 times 10 to the negative 3 coulombs. And that's going to be equal to delta V. So delta V is equal to negative 1.7 times 10 to the 6 Newton meters per coulomb, which is a volt. Okay, so now we know delta V. We can now use that to calculate our VF and our VI. So we know the distance that they were originally apart, so we can use that to calculate VI. So VI is equal to K times Q divided by R. 9.0 times 10 to the 9th Newton meters squared per coulomb squared times the stationary charge, 0.45 times 10 to the negative 3 coulombs, divided by R, which is, they were initially 0.33 meters. And so meters cancel one of the coulombs, so you're left with Newton meters per coulomb. So VI is equal to 1.2 times 10 to the 7 volts. Okay, so now we know delta V and we know VI, so let's use that to calculate VF. So delta V equals VF minus VI. So delta V plus VI equals VF. And we know we calculated delta V as negative 1.7 times 10 to the 6 volts. And we will add to that the VI that we calculated, which was 1.2 times 10 to the 7 volts. So VF is equal to 1.1 times 10 to the 7th. Volts. Okay, so now we have VF. That's equal to VF. Okay, so where do we go from there? We're looking for the radius. We want to know how far away this particle will move until it stops and turns around and goes in the other direction. So we know that VF is equal to 1.0 times 10 to the 7 volts. Well, now we can use our equation that V is equal to K times Q divided by R. This, in this case, will be the BF. So we're going to solve for R, multiply both sides by R, divide both sides by BF. So R is equal to K times Q divided by BF. So R, 9.0 times 10 to the 9th, Newton meter squared per Coulomb squared, times the Q, which in this case is the stationary charge, 0.45 times 10 to the negative 3 coulombs. And then now and then we divide that by the VF that we calculated, which was 1.0 times 10 to the 7 volts, which is a Newton meter per Coulomb. Okay, so these coulombs are all going to cancel, and the newtons will cancel, and this meter will cancel. We'll just be left with meters up there. So R will be equal to 0.41 meters. Okay, so what that means is that so these particles are going to start 0.33 meters away, and when they are 0.41 meters away, then this particle will turn around and it'll go back the other direction. So in other words, it will only move 0.08 meters. So it'll move 0.08 meters this way until when it reaches 0.41 meters, then it's going to turn around and go back the other direction. Okay, so I know those problems look long and they look complicated, but it's really nothing. It's just applying formulas that we have seen before. So I would like for you all to do on your own 14.5, 14.6, and 14.7, and we will start next week by going over those problems.